Today I'm going to be looking at centres of triangles, and I picked this triangle over here for my demonstration today. So as you can see, we can move points around to see what the result is. First centre we're going to look at is the circumcenter. So I want to remind you how you construct this. The circumcenter is constructed by bisecting any two sides of the triangle. So if you look at what I've done here, I've got a perpendicular bisector of these two sides, and wherever those two meet, it turns out the third one will always meet there as well if we go to the trouble of drawing it. Wherever those two meet is the circumcenter of the triangle at this point here. You'll notice that the circumcenter, it sounds strange, but the center of the triangle doesn't actually have to be in the triangle. In my example here, it's actually outside. As you can see, sometimes it's inside, sometimes it's outside the triangle. And we'll move on from that one. The circumcenter, we'll switch this one off. Before we do that, actually, of course, one of the things you can do with the circumcenter is if you get a compass and put the point of your compass on the circumcenter and draw a circle, it should go through the 3 points of the triangle, or the 3 vertices of the triangle. And there you see it, there's the circumcenter. So it's a circle that goes through all 3 points of the circle, of the triangle. Now, next one I want to look at is the incenter. Now, you got to be very careful in an exam with these centres of triangles, because it's the kind of thing you could just get two of them mixed up on the day very, very easily. So be absolutely clear before you go into any exam of what the difference is between each. The incenter, and I mean, it would be an awful shame if you went to the trouble of doing a perfect construction in an exam of, for example, an incenter, when they were actually looking for a circumcenter, or vice versa. So watch carefully. The circumcenter we just looked at was bisecting the perpendicular bisector of the sides. The incenter is the bisector of the angles. So if you move this around again, and you can see what I've done, I've bisected any two of the angles. So these lines are the angle bisectors, and where they meet, we call it that point the incenter. Now, unlike the last one, no matter what you do, you cannot. The incenter is always inside the triangle. And of course, associated with the incenter is the incircle of the triangle. So just turn that on. And this is a circle that touches each side of the triangle. It just touches each side. The next centre is the centroid. And again, please don't get these mixed up. You can see that the centroid has to do with the intersection. Sorry, it's from each vertex to the midpoint of the opposite side. So, for example, from the point C to the midpoint of AB, and also from the point B to the midpoint opposite. And where they intersect is called the centroid. Again, we can move this around. You'll notice centroid again is always inside the triangle. What's significant about the centroid, I suppose, is in the science world, it's called the centre of gravity. This is actually the point where, if you balance that triangle on your finger, if you cut it out in a piece of cardboard or whatever, that's the point that it would balance at. It's the centre of gravity of the object, of the triangle. It also turns out that there's a very handy ratio that can be useful. The ratio of the two lengths is always 2:1. So if you look at this length here, along here, and compared to this one down here, it's always 2:1. And the same here, this piece here, this line segment here, compared to this line segment up here, is 2:1 also. And the last centre you need to know about is the orthocenter. And the difference here is, as you can see, it's not easy to see because of the way the triangle is, but if I move this out a bit, the orthocenter is from each vertex. And if you just cut the opposite side at right angles. So if you drop a perpendicular from each vertex to the opposite side, then you've got your orthocenter. We'll fill that in there. And this is another curious one. So because sometimes, depending on what you do, the orthocenter can go outside the triangle. And likewise we can do for any point in the same here. You'll notice that it always goes outside at the point where the angle becomes 90. So don't be alarmed again in an exam if you actually are asked to construct the orthocenter and you find that in your construction it turns out to be outside the triangle. That's, as you can see, that's very normal for the orthocenter. That can only happen for the orthocenter, the first and last there, orthocenter and the circumcenter. So we'll switch that off. Now I'm going to switch all these centers back on and show the 4 centers together on one triangle. We're going to hide the construction lines for clarity. I'm missing one, yeah, the in-center. Okay. And again, just do the trial and error and see what happens with the centers. As you can see, occasionally the circumcenter or the orthocenter go outside. The other two never do. It might be interesting to try and figure out when exactly does the circumcenter go outside. We know that we saw that the orthocenter goes outside as soon as the angle becomes 90, as I'll show you there. But when does the circumcenter? What makes the circumcenter go inside or outside? What exactly is the condition for that to happen? So maybe if we just go back to the circumcenter for a minute again. Go back to keep it as simple as possible, just the circumcenter now on its own. And let's try and figure out what makes the circumcenter go inside or outside. We can see this more clearly if we just turn on the angles. And now we can see, hopefully, that the circumcenter, it seems to be on the triangle when the opposite angle is 90. If the angle goes above 90, the circumcenter goes outside. If the angle is less than 90, the circumcenter is inside. And that can be very easily explained by one of the theorems on our course, because if you turn on the circumcircle, you will notice that the circumcenter, basically when it's at the center of that circle, when it's the center of the circle, well, because of one of your corollaries of the theorem on your course, when you've got a diameter, which the side AC now is, AC is now a diameter, and that's a diameter because of a corollary to a theorem. The opposite angle is always 90. So it seems it is the case that is our cutoff point. That the circumcenter, when it's on the diameter, as you would expect, the opposite angle is 90. But when the opposite angle goes above 90, the circumcenter is now outside. When the opposite angle goes below 90, the circumcenter is now inside. One last interesting feature of all these centers is this. If I turn them all back on one more time. And turn off that circle again for clarity. Maybe turn off the angle as well. We don't need these now. And just take a quick look. And can we see any pattern? Is there any connection between these 4 centers? And you should see, it might become even more obvious if I turn off one of them. It seems there's an odd man out here. It's the in-center. If I turn him off, and none of the other 3, and you might notice something. This word comes to mind, the word collinear. It means they're all on the same line. And you can show that line. It's called the Euler Line. It's spelled E-U-L-E-R. It's called after a mathematician, a Swiss mathematician. And if you draw that line, you'll see that no matter what you do, the 3 centers are always on that line. Now, the 3 centers are on this Euler line. Can we go one better? Is there any way we can fit this odd man out in? This in-center. So let's put him in there and figure out what can we do to get him into this gang here of all the other centers. He seems to be fitting in there now. And what's the condition that makes him fit in? And you can probably guess already by the shape of the triangle if you turn on the angles and confirm it. this will always happen when you've got an isosceles triangle. So the four centres are collinear. The word is collinear. Four centres are collinear when the triangle is isosceles. And we can be more ambitious again, and we can see, is there any way at all that we can get the four centres even closer? Not just on the one line, but can they possibly be the one point? Can they all converge onto one point under certain conditions? Hard to get it exact there, but hopefully you can see the way it's going. If you can try and make your angle 60, if I can get them exactly to 60, or an equilateral triangle, we should find, under those conditions, the four centres will be the same point. So, a bit of a rounding off there, but so I suppose that's as close as we'll get. But you can see that you can get the idea that if we can make those triangles exactly 60, all of those four centres will then become the one point. There is no difference between them. And so to summarise, in a scalene triangle which has no sides equal, you'll find that you'll always have three collinear points. Yeah, no matter what you do, you'll find that three of the centres are always the same anyway. No matter what you do, those three centres, all of them except for the incenter, are on one line. We can go one step better, as I said. We can bring the incenter in if we make the triangle isosceles. So we've gone from scalene to isosceles, and we can go one better again, go from isosceles to equilateral. And if we can do that and manage that, make them all 60, as we saw earlier, they'll all be the same point. So that's the end of the lesson on triangle centres.